Good morning, good evening, everyone, and welcome to SETI Live. We are not live for this broadcast, but we are live from New Orleans for the American Astronomical Society AAS winter meeting. It's a great buzz here in the convention center, and my name is Simon Steele. I'm Deputy Director for the Carl Sagan Center at the SETI Institute, and here talking with Chenoa Tremblay, one of our SETI scientists, radio astronomers. So great to see you here on a very, very comfy couch.
Yes, absolutely.
How's the conference going so far?
I think it's going great. I think one of the really interesting things about this conference is there's such a huge diversity. This is talks not just about astronomy, but engineering, diversity, outreach, education. This morning there was a plenary talk about putting telescopes on the moon. There's just a huge amount of information and people around and wide variety of experiences and a lot of networking. You know, it's great to bring students and give them an opportunity to kind of see the diversity within our field and science. And I think it's just been great fun.
Yeah, definitely. And we had quite a thunderstorm last night, just adds to the dramatic effect of the whole place.
Absolutely.
So a press release about your observations have just come out in the paper you've just had published.
Yes.
We'll put a link into both of those into the chat here. Say a little bit about COSMIC, which is this project you're working on. And first of all, what does COSMIC stand for?
Yeah, so COSMIC is the Commensal Open Source Multimode Interferometric Cluster. So really, this is a lot of words to just say it's a big computer system that we have built on the back end of the historical Very Large Array telescope in New Mexico. Mm-hmm. This is a beautiful telescope. You know, it's still world class. It's been around since the 1980s. It's iconic in its Y shape. Of the distribution of the antennas. There's 27 of these antennas. They move. They have these massive movers, and so they take these dishes, which are 82 feet in diameter, and you can move them around on these specialty devices on railroad tracks. And there's just a huge amount of science that is constantly being done with this. And what we get to do is take a copy of these signals that are coming from each of these antennas and do SETI. So we get to process these signals. We calibrate them to make sure that they're of scientific quality and we know what these signals actually mean. And we can search for signals, signs that something else might be developing technology somewhere else.
Okay. So this telescope, and of course, for those of you who maybe slightly older, but if you're younger, definitely watch the movie Contact. With Jodie Foster, which of course has a very strong connection with the SETI Institute. Now they start off at the VLA, the Very Large Array, which gives you an idea of the scale. But of course at that point, there was no SETI, search for extraterrestrial intelligence, going on at the VLA. It was looking at black holes, pulsars, quasars, and so on, and mapping the universe, which is, we'll talk about that a little bit. But this is the first time that the VLA has been used as a SETI instrument.
Absolutely, yeah. It's historically very well known for understanding it's helping us understand, you know, how galaxies evolve and form, how stars evolve and form, how the gas and dust are forming things like stars. But now we're actually getting a chance to investigate the opportunities of development of technology or development of life, and its history or its potential for history within our cosmos and not just on Earth.
Yeah. Now this is, we'll say a little bit about the commensal part of this, because it's almost like you're not doing SETI observations. You are sort of sneakily looking over the shoulder, not sneakily, looking over the shoulder of the astronomer looking at quasars, say.
Yeah.
And the data is coming in for that set of astronomers who are analyzing, you know, supermassive black holes and things like that.
Yeah.
And you got the same data set. Tell us about the journey of those photons as they come into the telescope. What are you doing with them as a SETI observer?
Yeah. So the observers themselves get to choose the position of the sky what frequency or wavelength that they want to study their favorite object in that position of the sky. So we don't have control over that, but we do get to get a copy of the data, and we get to do our own thing with this. And what happens is the photons are coming in. This is a radio telescope. So this means that each of these light particles, there's a tremendous number of them. They're not particularly high energy. And so what we do is the antennas collect these photons. Essentially, we have to boost the signal from those photons so that it's not lost as it's traveling through the cables down to the control building from the antennas. And then what we do is essentially what this is doing is heating up electrons.
Okay.
It's heating up the electronics. And that's what we get as a signal. And we can translate that information into understanding whether it's imaging the sky or whether it's just understanding the amount of power that's coming from those photons. And that allows us to translate it out into the science.
Right. Excellent. So when you're looking at say, again, a quasar, which just to explain what a quasar is, if we're using that term. So this is a distant galaxy that has a giant black hole at its center, and as the material spirals in, the very strong magnetic fields create radio waves and everything. What you're looking for is a narrow band signal, like tuning in a radio, receiver to pick up your favorite radio station.
Yep.
So that's the quasar observations are taking a much broader spectrum of light. They're looking for a bunch of different frequencies, and you are searching for individual frequencies. Can you say how does that work? Because you're trying to do very different things with the telescope.
I mean, we don't know exactly how another civilization might be generating electronics or signals or things like that.
We're assuming, yes.
And so, but we have to kind of start the experiment somewhere. The problem is a very large one, if we think of every possibility.
Yeah.
And so what we try to do is looking for something that could not be generated by a standard physical process in the way that we understand fundamental physics. And so, so what we're doing is essentially, if you think of taking sunlight and putting it through a prism and separating out to the colors of the rainbow, we're doing, very minute shades of those colors, but using radio waves instead of optical light like you would through a prism.
Okay.
And so, by searching for something that is too narrow in frequency or too narrow in these light waves, that could not be generated by a physical process, we can immediately eliminate some aspects of the universe. And we're already eliminating what we interpret. It allows us to make it easier to interpret the data that we're looking for.
Right. So what is the width of frequencies that a typical VLA observation? Say a little bit about the spectrum, the radio spectrum that's coming in that you're analyzing.
Yeah. So a lot of times when people are doing imaging, this is what we call like broadband. So this is the emission is spread across a very large number of these frequencies or wavelengths. And so we average them all together and combine them all up, and then we can get the full information of what the radio light is doing or looking like or things like that. If we want to understand molecules or atoms, we can go into finer detail, but that's still kind of broadband when we think of electronic emission. But what we're talking about, if you think of it in a frequency term, is that a lot of times people are looking at images of, say, like quasars. They might look at 2 or 8 gigahertz and smoosh it all together for their information. If you're looking for information about the emission that's created from molecular interaction or atomic interaction, now we're looking at a couple of hundred of hertz or maybe a kilohertz. What we're looking for from a technological perspective is something that's emitting within a hertz or a subhertz nature, something similar to what's being emitted by electronic signals from the Mars, probes or orbiters and things like Voyager and things like that. We're sending those electronic communication signals even your GPS signal are these narrower signals, and those are the type of things we're looking for.
Right. Because I sometimes use the analogy of tuning in a radio, and again, this shows my age. One day analog radios will come back, where you do turn the dial and you tune into a transmission, a radio transmission. Then you hear the great music or less great music, and then you move on. Is that a good analogy? Obviously, that's turning radio waves into sounds.
Right.
And you're doing, a conversion as well. Radio wave energies into something that you can read out.
Yeah.
Is that still a good analogy for finding those narrowband signals?
I think one of the things that's challenging from these days is that a lot of times in our historical SETI experiments is that compute is our biggest challenge.
Mm-hmm. Okay.
How powerful are our computers, and how much storage can we handle?
Mm-hmm.
And so we actually had to very much narrow the search because we just couldn't handle too much information.
Yeah. Mm-hmm.
But when we've got something as powerful as Cosmic now, we can take in a lot of information.
Mm-hmm.
So we're taking in a whole gigahertz now, and we're searching it in small chunks. But it doesn't matter where that signal is. We're going to search the entirety of that piece of data.
Mm-hmm.
And then what we're doing in our system runs autonomously. It's all by itself. It's running in real time. That means that if I take 5 minutes of observations, in 5 minutes, I get the results out.
Right.
And then that information goes into a database. And so it's searching through all of that data for signals. And we have written a program that says, this is what the signal we expect is going to look like.
Mm-hmm.
Go find it.
Okay.
And then when it finds it, it pings it, puts it into a database of the characteristics of that signal.
Yep.
What does it look like?
Yep.
And then saves the raw data. So then scientists can go back and visualize that data through like Python programming or things like that, where we can go and then we can look and see what does that signal look like as a function of time and wavelength, and what is it doing, and does it look like something that is localized on the sky, or does that look like it's something that's generated here on Earth, or orbiting one of our planets in our solar system.
Yeah, that's and we talk about the huge data sets, but it's interesting is that, and of course here at the SETI Institute booth, we're surrounded by wonderful scientists. We've got a NASA booth over there. We got the Space Telescope over there, and of course, still even in this environment, the first things people ask, well, have you found anything yet? So presumably, as you say, the VLA and all radio telescopes like the ATA that the SETI Institute has is picking up artificial signals all the time, isn't it?
Yeah.
And so you need to. It's a needle in a haystack to even get rid of signals that are the signals you're looking for.
Yeah, it's a huge challenge, but everything is about learning and building upon those learnings and trying to improve the experiment as you go along.
Yeah.
And so right now, we take in way more data than is probably realistic, as far as these are all not going to be real SETI signals, right? They're not even necessarily candidates for SETI signals, but they're things that look kind of like a SETI signal.
Yeah.
So, for example, I took some time to point the telescope at Voyager, and our pipeline found Voyager.
Good. Yes.
That's what we
You found
expect.
intelligent life. Yes.
Yeah. But that's in a forest of other signals that we know are generated here on Earth. And right now, we're working on understanding the what we would expect from the telescope, what we expect from the local environment. We're creating a database of that information of what's the persistent signals that are just due to the natural environment around the telescope. Yeah. And then being able to say, okay, we already know that one is not SETI, and just eliminate those. And so we're improving that experiment as we go and as we learn to make things better.
Okay. So how much data are you getting, and where are you sticking this data? These telescopes are picking up a lot of information.
They are.
Give us an idea of how much, how many floppy disks, are you filling?
Yeah, so I think at the moment, we're generating between 5 and 30 terabytes of data a day.
Okay.
That's how much we're saving. So we throw out a lot of data because the pipelines go through, it filters out the data, it looks for these signals, and only saves where it thinks a signal exists.
Yeah.
And that's still, so we're intaking as part of the pipeline, we record something like every observation is about 2.5 terabytes to 5 terabytes.
Okay.
But then it saves only a few hundred gigabytes of that data.
Okay.
And so what's going through our system and then what we're actually saving in the end are different things. But we can think of it this way, is that the information coming in to our racks is about 2 terabytes per second. That is taking like the entire HBO series of Game of Thrones, the entirety of the series, and streaming it every single second.
Yeah.
And that's the information that's coming through. And that's why it's not realistic to save everything. And so we have to put these filters in place. We have to have, at the moment, have some way of going, I'm going to look for this style of signal today.
Wow. Yes.
And but the system is completely designed to be modular. Somebody else can come to us and say, you know what if the signals looked like this? Tell me what the algorithm is, or tell me what it is that you think it would look like. We put that software in for a bit of time, and we store that data, and we say, okay, now you can go look at this. Did you find that style of signal? So having it flexible and modular will allow us to not just do SETI in the future as well, but search for other styles of signals and other scientific endeavors as well, which is really exciting.
Having that flexibility to evolve over time, both in terms of speeds and capacities, but also in terms of the methodologies of search. Makes it very, very powerful. Yeah, nice. So, obviously, you're not pointing the telescope because somebody else is doing that. What is the VLA, or what has the VLA been looking at in the sky that you've been able to collect data for? What are they doing?
They're doing stuff all the time, obviously, and the currently Cosmic is still in its infancy. So we can't observe with every single style of observation, but we're observing about half of the time that the telescope is operational at the moment. And we've been seeing that there are surveys of like the local group of galaxies. So around the Milky Way is a number of different we've got Andromeda galaxy, but there's a lot of dwarf galaxies. There's ones that don't have black holes in the center. They're just made up of lots of stars and dust and gas. And there's about 12 or so prominent local group in our local group. And so people have been studying those. And so we get to see those patches of sky. But really what it doesn't particularly matter what the main science that they're looking at. So what we're doing is that we have a database of stars. And we have gotten this from the Gaia probe. And we've what we do is that with every patch of sky, we choose 5 of the closest stars to us. And we essentially can mathematically point beams at each one of those positions and collect the information towards those. And then what we also do is then sum all the information across the sky that is observable by that pointing. And then we can look. So we're not only just targeting stars and potential solar systems, we're also just going, well, we don't have to know where it is in the sky. We're just going to average across the whole sky and look for something bright. And so adding those 2 bits of information allows us to really search a tremendous amount of the observable universe. So
not only you've got the broadband search of the sky, but we now know about exoplanets around nearby stars and everything, and those are obviously prime candidates just to pick out as you move through.
Absolutely.
So you say this is just the beginning. Where now? I mean, this program is ongoing. How do you see it evolving over the next few years?
I mean, I think one of the great opportunities that we've had is to be able to observe along with the Very Large Arrays program, the NRAO's program for their All Sky Survey. And so they're mapping everything that can be observed from the view of the telescope. So obviously we can't see through the Earth, and so we can't see every part of the sky, but they constantly are slewing the telescope across and mapping the observable universe from the telescope's perspective. And so we get to tag along with that. And so this means that for the first time, we're able to do a SETI search that covers everything that is observable from the Northern Hemisphere and from the telescope's position. And that's not something that has been done before. And the downside of that is it tends to be shallow. So that means that something would have to be pretty bright for us to detect it.
So shallow because you're not looking at it for very long, because you're just going
Exactly.
across, and it needs to be, you know, in your face almost to actually detect it.
Yeah, absolutely. But it means that we get to cover a lot more of the area, and we know the spatial dimension is one of those aspects of SETI. Like, where is it? You know. Well, this one we get to map everywhere, and the where is kind of taken care of. And you know, we've got currently we're working on scrolling through all of the data that we had taken during this first aspect of the epoch of the survey. And so our database contains information at almost 500,000 sources at the moment.
Wow.
And we still got a couple more months of data to still collect into the database. And so we're still reviewing that. And so I think we're going to start filling in the sky pretty quickly.
Nice.
And then the second epoch of that survey starts again in May. And so we'll be back on Sky all the time again for that. And continue to kind of fill in the rest of the patches.
Okay. So I do have to ask. So, you know, you're doing these observations. You're sifting through the data. You're removing, you know, the Voyager signals. You're removing, you know, the satellites and the airplanes and everything. What happens if you get a signal that meets all the criteria for a potential techno-signature that's non-human? What is the procedure at that point that you go through, apart from taking a deep breath and lying down?
Well, I think one of the things that's really important is confirmation. Right? You know, it's not impossible to miss something, you know, misinterpret something. And so repetition is going to be a big deal. So with our pipelines, and if it flags something of particular interest, then what we have is proposals that we have submitted. So telescopes around the world have agreed that if we find something, they will help hand over the telescopes to us, and we're going to go back and look at it. If we can get various telescopes around the world to see the same thing, I mean, that's your confirmation right there, right? You don't have to worry about whether it's an aspect of your electronics, your telescope, your pipeline. We've got you know, different computer systems, different telescopes, different electronics, and if they still see it, then that would be an amazing result. And so that would give us that confirmation. And so that's what we've done, is that we've got the Very Large Array was agreed to just turn it back over to us. There's two independent data streams there. There's the cosmic one and the standard one that the scientists use. We have the Very Large Baseline Array, the VLBA, which is 10 telescopes situated around across the US. Which would allow us to potentially localize the signal, figure out where it actually is coming from. We've also got the Parkes Radio Telescope, the 64-meter dish that is in Australia, and the Green Bank Telescope in West Virginia, as well as the Allen Telescope Array in California,
in our own backyard. That's good. Because, of course, the point of the real science of extraterrestrial searches is you need to tell everyone, because you need these observations to be replicable. You need to be able to follow them up and rule out any other possibilities before you actually say, look, we found something. And that's, you know, that's the real way to search for aliens.
Absolutely. Scientific process is definitely important.
Absolutely. It's been wonderful talking to you. Did you ever think that you would be involved in SETI searches? Was this your aim when you got into astronomy, or?
I've actually, part of my PhD was in SETI. Actually, so I've quite enjoyed this. I mean, this is a phenomenal question. It's an important question, and the fact that now we're able to do this at the same time as answering other questions about our universe is just a fantastic idea. You know, no one's giving up anything. You know, we're doing it. We're understanding. We're learning. It's been an amazing experience to be able to work on Cosmic and build it from its ground up and be part of this project. I think, you know, I've learned a lot more about not just SETI and
Mhm.
its science, but I've learned way more engineering, computer skills.
Maybe more than you care to, I do. But yeah.
I mean,
Yeah.
and it's been a fantastic group to work with. They've been really helpful in helping me build that learning, and so I'm really excited for where it's going to go in the future. I hope we can within the next couple of years really kind of fully build it out, take full advantage of the telescope and its capabilities, and make this as much of a world-class experiment as the telescope and its history.
Okay, great. Thank you.
Thank you.
Thank you, everybody, for tuning in. Obviously, we'll be following the Cosmic program very closely, and we'll have another conversation maybe in about a year or so and see where things are, or earlier if something happens.
Yeah.
Check out our website, SETI.org, and that'll give you all the information about the latest science that's going on, and sign up for our newsletter, which will give you updates on all the programs, including the Cosmic program. Thank you very much for watching.